All right, so what I want to do is just finish off this course by giving you an idea of where things are going. So what we did in finite element method, mesh-based approaches, what you can do next semester with finite volume approaches, all mesh-based approaches, and that's sort of, I'd almost want to say, starting to die out slightly. And the reason that they are dying out is different computing devices are available. So what I'm going to do is I just want to introduce you to just the difference between what a CPU and GPU is, and why pretty much all the research that I do is focused on graphical processing units, where we use essentially the GPU that you used to play games with to actually do science with them. And so, I can't recall if I've played this video in the beginning of the semester or not, but this video will just, for those of you that have forgotten about it, if I've shown it, remind you what the difference is.
All right, I introduced you Leonardo, and he's going to paint a picture for you guys in the way that a CPU might do it, as a series of discrete actions performed sequentially, one after the other. In 3, 2, 1. Let me speed it up. Ladies and gentlemen, Leonardo. When we hit this trigger on this thing, 2,100 gallons of air goes through these accumulators, out these valves, into all 1,100 of these tubes, into these tubes within which the bottom of is a paintball. Each of those paintballs will fly across 7 feet of space and in 80 milliseconds reach its target, hopefully. When it's all said and done, it's going to paint the Mona Lisa.
GPU painting demonstration.
Yep.
And
10, 9, 8,
7, 6, 5, 4, 3, 2, 1.
Ladies and gentlemen, science class is now over.
So hopefully that would just give you an idea in terms of where things are going when it comes to GPUs. And the kind of solvers that work well on GPUs are what's called particle-based solvers. So I'm just going to give you a flavor of what they are and what kind of research we're doing at the moment at Techies regarding computer-aided engineering or solving these things. And we do a lot of machine learning, AI, generative modeling on top of this. But this is just to give you a flavor of, I think, where a lot of this technology is going. So here's just a couple of examples that I'm going to show you. So the first one I showed you, there was sort of a heat example of a lid-driven cavity heat pump. So they essentially heat at the top, and then it starts to induce sort of a cavity kind of flow. And these are, you can see, discrete particles. There's no mesh involved. This is essentially how this would work. Okay. The reason why it's important to take note of what's out there is that essentially these things allow you to do lots of multiphysics in a nice and easy way. So if you just open up this, is my dam break one, yeah. So this is just a normal CFD flow simulation. No other physics involved here, but this is essentially just a normal dam break. One of my PhD students, Johannes Hubert, that is developing particle-based solvers for that we can couple in the end with discrete element modeling. So we can very easily then extend these flows to interact with rocks, for instance. That's an example of that. This has been used practically with our collaborations with Tsinghua University in China. Here's an example of just how, for landslides, in essence, where you have these rocks that are interacting with sort of the water. And the reason for why this is important is there's something called landslide tsunamis. So when a wall or something collapses, a part of the mountain collapses into a dam, you create huge waves. I mean, a couple of 100 meters high, lots of impact, lots of chaos when those things hit land. You can also just model, essentially with particles, you can also just model material, raw, dry material, or cohesive materials in mixing processes to see what that is all about, how that interacts and how that works. So this is really just to give you an idea of where things are heading and what are the things that we are busy with. All of these things that you saw are running extensively on multiple GPUs. Okay. And take note that there's lots of new technology coming out from industries. And as I've reminded you in the beginning of the course, why it's important that we do validation verification is, here's just a last example again of a commercial code doing discrete element modeling. And there's lots of non-physical chaos here. And so be aware that a lot of these technologies are getting pushed, so it's going to show it again, are getting pushed into packages, but still your job as an engineer to make sure you trust it. Just because it's in a package doesn't mean it's correct. So I'm just going to highlight again what are the chaoses that you can see here. So essentially, if we run it again, you can see there at that lifters there on the right, bottom right, there's lots of movement. You see that breathing of that whole pack. That's a lot of instabilities that's happening. And so please take note, verification, validation remains your responsibility. All the best with your careers, and I look forward to see those of you that end up with me with MRN next semester. Goodbye.